Previously, we had looked at section 9.2, which was tests involving the mean for a large sample. Today's lesson is how this method is changed when we are looking at a small sample. And why would we have to worry about a small sample? Let's just get more data. Well, the problem is that a large sample that's approximately normally distributed isn't necessarily available to us. It might not be practical to get that much data. It might be too expensive. It might be too time-consuming. It just might simply not be possible. And we can still do hypothesis testing. We just have to change our methods just a little bit. We welcome back Table 6, Students' T-distribution. We are replacing the standard normal curve with a T-distribution. Again, there's many T-distributions based on the degrees of freedom. So yes, we do need to emphasize the size of the sample in all of these problems. And that means that, again, we're referring to Table 6, and now we get to use the much ballyhooed alpha prime and alpha double prime rows at the top of Table 6. Remember that before in the heading we focused on the row labeled C, and we kept the alpha rows. We said we're going to set those aside, we'll deal with those later. Now's the time for us to deal with them. When we are doing a one-tailed test on a small sample, regardless of whether it's a left-tailed test or a right-tailed test. In other words, regardless of whether the alternate hypothesis is a less than statement or a greater than statement, in that case we're going to use the alpha prime row. This is for when we are doing a significance test based on a one-tailed test. When we are doing a two-tailed test, in other words, when the alternate hypothesis is something in regards to mu being not equal to a number, that's when we will use the alpha double prime row. And as I said before, we are still using n-1 for the degrees of freedom. So degrees of freedom are still at the heart of what we're doing here. So for a left-tailed test, alpha prime is the blue shaded area in the left tail. And as a result, because we are talking about a t-score that is lower than 0, our critical value is going to be negative. So in this case, t sub 0 is always somewhere below 0. For example, we might be targeting t sub 0 being negative 2.093. Emphasis on the negative. Similarly, for a right-tailed test, alpha prime represents the area in that blue region over in the right-hand tail. And since we are talking about values of t that are greater than a positive threshold value, for a right-tailed test, t sub 0 is always greater than 0. For example, we might be comparing a test statistic t with a t boundary of positive 2.093, to use the same number that we had used before. For a two-tailed test, again we're using the alpha double prime row here, and that's the area that is to the left of negative t, so the area that's over here in this left-hand tail, and the area that is greater than the positive t-score. So if we're in either spot, then we're in one of those blue regions. And because the t-distribution is symmetrical, we're also able to say for sure that half of the target area, half of alpha double prime, is the area in the left tail, and the other half is the area of the right tail. Oh, my animation didn't work right, but that's okay. If we are looking to find a critical value for t sub 0 for particular test, let's say our sample size is 11. If we have a sample size of 11, that means that we have 10 degrees of freedom. So we want to be in the row df equals 10. And a right-tailed test, that means that we're interested in alpha prime, and at a significance level of 0.01, we will go to the column for which alpha single prime is 0.01, and then go down to the row for 10 degrees of freedom, and we find that the critical value, the target value that we're trying to exceed, is positive 2.764. Similarly, for a two-tailed test, anytime we see two-tailed tests, we know that we are working with alpha double prime. With a significance level of 0.01, that's going to put us over in the far right column. Again, we still have 10 degrees of freedom, so we slide on down to the row for 10 degrees of freedom, and we find the number 3.169. Anytime that we are discussing a two-tailed test, the sign on the critical value is the plus minus symbol. So it's plus or minus 3.169. We will reject the null hypothesis if the t-score that we come up with in a moment is greater than 3.169 or if it's less than negative 3.169. If we get either one of those to be the case, then we have landed in one of the two shaded regions, and as a result, we would conclude that we would want to reject the null hypothesis. Our test statistic is t. It's the same t we've been using before, x bar minus mu in the numerator and s over the square root of n in the denominator. That's not anything new. So let's do an example problem. A company manufactures large rockets used to project satellites into space. NASA requires that the rockets use an average of 5,500 pounds of fuel during the first 15 seconds of operation. That 5,500 is probably pretty important to us. The company claims its rockets fit specifications, which is good. They all claim that. But we're going to test that. To test this claim, an inspector randomly selects 6 rockets, each of which is fired for 15 seconds. The mean fuel consumption for the sample was 5,690 pounds with a standard deviation of 250 pounds. Is the company's claim justified at a 5% level of significance? First, let's set up our hypotheses. Our null hypothesis is that, yeah, the claim is what it is. Based on this sample, we are going to conclude that the mean is actually 5,500 pounds worth of fuel. The alternate hypothesis is that it is not. There was nothing in the description of the problem that said that it was greater than 5,500 or less than 5,500. It's just the specifications say it should be burning 5,500. So we will conclude that anything that suggests that the mean is not 5,500 pounds is a problem. And that causes us to have the not equal to, that mu is not equal to 5,500 pounds. What test is performed when we have a not equal to? That would be a two-tailed test. Because we are working at a 5% level of significance, that further tells us that alpha double prime needs to be 0.05. So from that, we'll ask the next question: what is this critical value? What is this boundary that we are trying to get past? Or actually, there's two boundaries, because this is a two-tailed test. One boundary is negative, the other one is positive. At a 5% level of significance for a two-tailed test, our student's t-distribution table tells us that the value that we are looking to exceed is to go either lower than negative 2.571 or larger than positive 2.571. We then find t. We have x bar minus mu in the numerator. 5,690 was the sample mean. 5,500 was what we're expecting mu to be. The denominator is the sample standard deviation, 250, divided by the square root of the sample size, divided by the square root of 6. And when we do that calculation, we find that our sample, our test statistic, t, is 1.862. Does that put t in one of the critical regions? Does that put us in the left tail? Does that put us in the right tail? The answer is no and no. We're in the massive middle of the t distribution. We did not hit the left tail. We did not hit the right tail. We had a positive number, so let's not even positive number for t. So let's not even worry about the negative. The problem is that 1.862 is not greater than 2.571. We did not get into the right tail. We obviously didn't get into the left tail either, and so as a result, we fall outside of the critical regions. We fail to reject the null hypothesis. And we put this back into words. Again, we always put this back into a statement of what the problem was, and we say that there is insufficient evidence. There is not enough evidence to indicate that the average fuel consumption from the first 15 seconds of operation is something other than 5,500 pounds. If it is, we don't have convincing evidence of it at this point. Let's do a related example. Suppose that the previous inspection was conducted with a random sample of 8 engines with a mean fuel consumption of 5,880 pounds. We'll say that the standard deviation is still 250 pounds. Use a 1% level of significance to test the claim that the average fuel consumption exceeds 5,500 pounds. So some important information here in this problem. Embedded in here we have a value of n. Our sample size is 8. We have a value for x bar. We have a value for s. And we are asked to take those numbers, put them together with our claim about 5,500 pounds in order to test the claim that the average fuel consumption, is in excess of 5,500 pounds. So give this problem a try, and we'll come back together and we'll solve it. So first off, we needed to state the null and alternate hypotheses. The null hypothesis is that mu is equal to 5,500 pounds. The alternate hypothesis is that mu is greater than 5,500 pounds. And that part's coming off of the word exceeds. The fact that the average fuel consumption exceeds 5,500 pounds, according to this claim, tells us that we need a greater than. That means a right-tailed test. And since we're doing a single-tailed test at a 1% level of significance, Table 6 indicates to us that the critical value, the boundary value that we need to exceed is 2.998, just about 3. When you go and test that, though, you found a t-score of 4.299. That's coming from the 5,880 minus 5,500 over 250 divided by the square root of 8. And that gives you 4.299. Because our t-score was more extreme than the critical value, we are going to reject the null hypothesis. And we will conclude that we have enough evidence to show that the average fuel consumption is in excess of 5,500 pounds. Here's some practice problems for you. And for all of these, part A is asking you to take a calculator and verify the sample mean and the sample standard deviation. We don't need to do that. We're focused on hypothesis testing. So for all 4 of these problems, skip part A. Just assume that what they're telling you that it is actually what it is, because they're not lying to you.